Okay, so we left the last video talking about how we know, and I think that's a great question to ask. And so let's look at how they know. All right, so this is kind of the collection of information that we have going back millions of years. I find this part of it very interesting. A lot of this very ancient, millions of years ago data back here is from ocean sediments. And so they are able to get information from that. But we're going to talk more about what's happening here. If you look at our average temperature, of course, this is the very beginning of the Earth. I don't think much life was here at this time. So as we approach that temperature, we need to remember that although we've been here before, it may not be a world that we are interested in inhabiting. So we are really on the edge of seeing some unprecedented data. Okay, the first one that I want to talk about is how do we know, is what are called ice cores. Because we didn't have thermometers back then, didn't even have people back then, how do they know what the temperatures were? These ice cores are from mountains and glaciers, and they go back hundreds or thousands of years. The oldest is 800,000 years old. That's in Antarctica. And let's look at a video about this. I thought this was super interesting. It's just a short little video that will help you understand how in the world they were able to look at this.
At the National Ice Core Lab in Lakewood, Colorado, a giant freezer stores over 45,000 feet of ice, drilled from 34 sites around the cryosphere. Dating back hundreds of thousands of years, these ice cores are time capsules that allow scientists like Jim White to peer deep into the history of ice.
This piece of ice is interesting because it has a couple of things you can see right away. One is there are bubbles throughout here. These bubbles are little packets of air. It's these bubbles we can take out and measure CO2 and methane and nitrous oxide. It's the only medium that really collects the atmosphere itself. The other thing you can see in here quite clearly is you can see the layers. And the thickness is going to tell you how much snow fell that year. So you get a couple of pieces of climate information and the dating scale just out of visually looking at this ice core.
Most importantly, scientists have identified a direct historical link between increases in greenhouse gases like carbon dioxide and steep rises in global temperatures. At every peak, big rises in sea level followed as Greenland's ice sheet shrank. The ice core records also reveal a particularly telling moment in Greenland's history. Roughly 125,000 years ago, temperatures rose by about 7 degrees Fahrenheit. The entire southern portion of the ice sheet melted, and global sea levels rose by over 10 feet. It was caused by a change in the Earth's orbit around the Sun, which increased temperatures and released carbon dioxide from the oceans. The more recent ice core record shows the potential for a similar meltdown. Right now, greenhouse gas levels in the atmosphere are even higher than they were 125,000 years ago, higher than they've ever been in the last 500,000 years. Temperatures are already following suit. The only explanation is the burning of fossil fuels.
What we see in this ice core is very solid evidence that what's happening today in the atmosphere is different. It's not a normal part of the climate cycle. It's something caused by human beings.
Rising temperatures are once again pushing Greenland towards a major meltdown. But what the ice cores can't tell us is how long it will take. The last time Greenland lost a significant portion of its ice, White suspects it happened over thousands of years. But this time, it could happen much faster.
So really important pieces of information about this, these ice cores. These were very interesting to me. There's preserved air that existed thousands and thousands and thousands of years ago. In that air, we can determine the concentrations of carbon dioxide. And we can compare them to ice cores in the present, where we know what the temperature was based on the concentration of carbon dioxide and other thermometers, etc. We know that information, and we can extrapolate into the past. So how do these things work? So let's look at this. All right. This is kind of a really interesting picture of them. You can really see the bubbles in these ice cores that they're collecting. The best ice cores are taken from places where the snow doesn't melt, of course, so it just layers. Ice cores are generally drilled from Antarctica and Greenland. The oldest ice cores date back to 800,000 years ago. Ice core layers are similar to tree rings. New layers form on the top of the last year. When analyzing the layers, winter snow layers appear lighter than summer snow layers. This is because the snow melts slightly in the summer, refreezes, and is more dense. When we count years in an ice core, a light band and a dark band make up 1 year of snowfall. As snow falls, particles from the atmosphere get trapped in the snow. You can see ash from volcanic eruptions, pollen, and even radioactive atoms to make inferences about what occurred that year. Air bubbles are trapped in ice core layers. Scientists can melt these and collect them. Another way that we can look at old climate data are tree rings. Interestingly, with dendrology, we can look at tree rings in a couple of ways. We can look at the space between the tree rings, so you know that if it's a really thin amount of growth, small amount of growth, that's a drought year. But if it's really wide, that's a good year. Some trees go back, hundreds of years back into the past, and by analyzing their tree rings, you can look at what happened that year in climate. Another couple ways that we can do this is sediment, especially ocean sediment that is deposited on land and stored for extended periods of time in lakes, bogs, and pond sediments. Basically, we can look at biological material by looking at carbon-14 data labeling. We can look at how old the pollen is, and then we can look at the quantity. We can look at the type of pollen. Certain types of pollen are going to grow in wet years, other types are going to grow in dry years, and we can look at all of this material in the sediment and get kind of an idea of what was happening in climate. Pollen can be done as well. Coral skeletons have calcium carbonate that is also carbon in them. It also contains oxygen. Interestingly, one of the things that I find fascinating is that they can actually look at the ratio between oxygen 16 and oxygen 18 in things that contain oxygen, and they can determine the ratio will tell them what the temperature was in the atmosphere at that time. Kind of complicated. I'm not sure I totally understand it, but they are able to do that with very good accuracy, and they can actually create these ratios in the laboratory and determine what the temperature was based on how much oxygen 16 and oxygen 18 that they have. So when you look at this whole picture of how we have put together this information, I think we have a couple takeaway lessons here. We know that there are only 3 ways that the Earth can heat up. Well, first of all, we know the Earth is heating up because we're measuring the temperature. So we know that. I don't think that's disputed. I think what's disputed is whether it's anthropomorphic, which means the dispute comes as to whether man is causing it. But we know there's 3 ways that the Earth can heat up. One from the sun, but all the studies with solar irradiation and monitoring the temperature of radiation coming from the sun says that that irradiation is not changing in periods where our temperatures are going up. So we've kind of discounted that. Or it could be something internal, but we talked about the fact that there's not enough energy for that. So it does have something to do with what's in the middle, and that's our atmosphere. So what scientists are doing is they're trying to now develop models. These are computer programs which are looking at all this data that you see here. How much carbon dioxide was there at this temperature? How much carbon dioxide that was there at this temperature? And they're also looking at the rates of the increase of carbon dioxide in our atmosphere and are trying to predict where we're going to be by 2050. And what we're going to look at tomorrow is thinking about where we could be in 2050. Do we want to do something about this today? So we will talk about that this week.